All right. Does everybody have a margin of error calculated for your sample? Yes, no. Okay. Critical value should be 1.96 for everybody. Your standard error is going to be unique to you and your partner. And then you have your margin of error. Yep.
The critical value, like those percentages are always the same?
Yep. Those are always going to be the same. You do not have to memorize those, but you should know how to find them. This one you'll probably end up memorizing because it gets used so much. But if they ever give you a different confidence level that they want you to use, we'll talk here in just a little bit about like what should you remember about how to put it in the calculator. All right. So I want you now to find a 95% confidence interval using your point estimate. So point estimate plus or minus the margin of error. So for me, that would be 0.26 plus or minus 0.1215. I want you to do it for your point estimate and your margin of error. Yours is not going to be 0.26. Yours is going to be whatever your point estimate was from yesterday. And then your margin of error is not going to be 0.1215 like mine was unless you had the exact same point estimate. It should be unique to what you had. I'm going to give you guys a moment to calculate your confidence interval because you're going to come up on the board and you're going to graph it here in just a moment. So remember to calculate that confidence interval. You take your point estimate minus the margin of error. You take the point estimate plus the margin of error. So mine, oops. Scoot mine down a little bit. There we go. So for mine, I got 0.14 to 0.38. It's fine to take it to just 2 decimal places, yeah. You have to add whatever your margin of error was to your point estimate, and then you have to subtract. Subtract for the smaller, for your lower bound, add for your upper bound. Does everybody understand what we're doing for confidence interval? Did you have a question? I'm going to show you how to do that. All right. Please make sure that you're not just copying the numbers down from my screen because your numbers are going to be different unless you have the same point estimate. Okay. We're going to come up and graph our confidence intervals. So mine is 0.14 to 0.38. Pop that up on the screen so that we have plenty of room. We're going to do these like in descending order here, so yours should not be side by side with anybody else's. You should go below the person that went before you. Do you guys remember when we did that activity on the computer the other day where we saw confidence intervals graphed for the first time? It should look like that. When we had that whole string of confidence intervals down the screen, that's what ours is going to look like. 2 decimal places. So go ahead and get this sketched into your notes. What kind of a confidence interval were we using again? 95%. So looking at where these confidence intervals ended up, where do you think the true proportion of kisses that land flat actually would be? So 0.30 would be like this. 0.35 would have us right here. Which one do you think it's closer to? 0.30, 0.35. If you had to pick one number, if you had to make a guess, where would you put the true proportion of kisses? 0.35? It looks like it hits or almost hits every single one. There's just that one that it might not be grabbing. I don't know exactly what that particular confidence interval is, but yeah, it looks to be, from what we've got, about 0.35. Almost every single confidence interval captures that. We believe the true proportion is about 0.35 from what we see. So once you have this sketched into your notes, we're going to go ahead and flip over to page 9. This is going to wrap up what we were working on yesterday. So when we are doing confidence intervals, we have to check our conditions. How many conditions did we have again? 3. I'll go back. We have to check for random. You're usually going to be pulling a quote from the problem stem to show that something is random, but you have to point to the evidence that you're using. You can't just say random, check mark. Why are you able to say that? What are you pointing to? What are you seeing? You have to provide that evidence. Just like if you're writing a paper, if you make a claim, you have to cite a source. Same kind of thing here. You're making a claim when you're checking this condition, and you have to cite where you're getting that from. Thank you. You have to check your 10% condition. What is it that we're checking for when we do a 10% condition? Independence. From what I have seen and the feedback that I have heard when they grade the AP exam, they want to see that you're checking for independence. You know you need to use the 10% condition to do that. So usually when I write this down anymore, I write both of those, like independence, so IND/10%. That way I'm showing that the 10%, I know the 10% condition is checking for independence there. And then we have to check for normality. Because we are working with proportions, we use large counts to check for normality. When we're working with means, does anybody remember what we use then?
Central limit theorem.
Central limit theorem. Is it 30 or bigger? When we have proportions, you have to use large counts. Even if your sample size is enormous, you still have to check large counts for normality. Critical values. These are the most commonly used critical values. 1.96 will probably end up getting stuck in your head because that one gets used the most frequently. But to find any critical value, you're going to use inverse norm of one of the tails. So 1 minus whatever your confidence level is, and then cut it in half because you've got equal sized tails on either side. You want just one tail. When you do it like this on your calculator, it's going to give you a negative number. Is your critical value ever a negative? No. It's just telling you how many standard deviations away you are. If it's negative, it's just giving you the one on the left. Should be exactly the same as if you chose to do the one on the right, but there's not a quick, easy to use formula for that one. And then formulas for confidence intervals for P. Point estimate plus or minus margin of error, or P hat plus or minus Z star times the standard error of P hat. So the square root of P hat times 1 minus P hat over N. They absolutely want to see this on the AP exam. When you are calculating a confidence interval, or we'll use the same kind of thing later on when we learn how to do what's called a hypothesis test, they want to see what are you using to set this up? Do you know the formula that you use to actually do this with? So these are things that you're going to write down. Don't just know them, get in the habit of writing them down. All right? Go ahead and give the check your understanding a try. got 4 pieces on it. I'm going to give us about 5 or 6 minutes to work individually, then I'll check in and kind of see where we are. All right, let's see kind of where we're at, and we'll baby step our way through this one. We're going to keep practicing with this because this big idea is part of that 4-step process. Do you guys remember yesterday when you picked up the new homework and there was one page that said the 4-step process page? These are pieces of that 4-step process. All right, so let's start off with what is the parameter of interest? Ben. Close.
Kids nationwide under 12, what kids under 12 nationwide want to be?
Close.
P equals the true proportion of kids under 12 who want to be a doctor.
That's it, right there. So you have to start with what the parameter is. In this case, it's P, not P hat, because P hat is a statistic. You have to put this down because we're going to talk about proportions and we're going to talk about means. So when you put P, you are communicating to whoever is reading this that this is a proportion that we are estimating. So P is equal to the true proportion of kids who want to be a doctor. Yes? You have to put down the P. Because when we do means, which will be next chapter, we're going to put mu, which would be the true mean or the true average of whatever. So yes, you do have to put P, true proportion of kids that want to be a doctor. Check if the conditions for constructing a confidence interval for P are met. If these conditions aren't met, we can't do any of the rest of the problem. I guarantee you on the AP exam, you can do the rest of the problem, but you still have to go in and check your conditions, and you have to show that you know you have to check those conditions. What are those 3 conditions? Random, 10%, because 10% is checking for independence, and large counts. When you do large counts, what are you checking for? Normality. Do we meet the random condition? It says it in the paragraph. Specifically, what does it say in that paragraph? It says random sample. Random sample of 1,000 kids. You have to provide that, like, quote there.
Oh, you can't just say random.
I mean, you could just say random sample because that is a direct quote from up here. You can, yeah. Usually it's going to be easier to just straight up quote whatever's in there. But if you says random sample, like if you were to write that, that would be sufficient. That shows that you went in and you read that in there and you're pulling that directly from the questions down. 10%. Do we meet our 10% condition?
Yes.
Yes, because there's at least 10,000 kids in this country. So 10%. All kids nationwide would be our big N. There's at least 10,000 kids. Do we meet our large counts? Yes. We have to do N times, can we do N times P here? We don't know P, so we have to do N times P hat. What is P hat on this one? 0.055, because it said 55 out of those 1,000 kids said they wanted to be a doctor. So we do 1,000 times 0.055 and 1,000 times 0.945. That's 1 minus P hat. We get 2 numbers that are bigger than 10, so we're good to move on. What is the critical value for a 98% confidence interval? 2.326. I think I rounded mine to 2 decimal places. But if you take it out to 3 decimal places, that's usually preferable. I was getting lazy writing my answer key, sorry. So let me pop that up higher on the screen. You do inverse normal of 1 minus whatever you want that confidence level to be. Cut it in half because it's split equally between those 2 tails. When you do that in your calculator, though, when you do inverse norm of 0.01, it gives you a negative back here, but that's just telling you that it's that far away on the left. Never have a negative critical value.
So I rounded up to their decimal, as long as you like put it on there so they can see where the numbers. So.
Yeah, so your numbers are going to be just a little bit different than mine, but they're going to be close enough. Because when you're grading, when a reader is grading the AP exam, They have a range of values that are acceptable, depending on where you round to. Okay, so now what do I do with that? .055 plus or minus.
Whatever your point estimate was.
Yep. Except there's one more piece. You have to take that critical value, 2.33 or 2.236 or 326. You have to multiply it by this guy right here. Does anybody remember what that square root with the p-hats is called? Standard error, which is exactly the same as standard deviation. You calculated exactly the same as standard deviation, so why don't they call it standard deviation? You have to have the true proportion to find standard deviation. We don't have the true proportion. That's the whole reason that we're doing this, is to try to figure out what that true proportion is. And so we have to use the point estimate that we found. So I have 2.33 or 2.326 times the square root of 0.055 times 0.945 over 1,000. Yes, the z thing right here is this critical value. It's what you get from doing inverse norm. Yes. Yes. Yes, it'll give you a negative, but a critical value is never negative. It's always going to give you a negative back on the calculator when you do something like this. You just need to know that it's not actually the negative. So I got 0.017 as my margin of error if I take it out to just 3 decimal places. You should get something reasonably close to that. And then to find that confidence interval, you need to subtract for the lower bound and add for the upper bound. 0.038 to 0.072. And now for the money question. Money. This is literally what will make you money. Interpreting that in context. That is great that we found this. Programs can find that, right? You could write a program, or someone could write a program to do all of these calculations, pop out that confidence interval. A CEO grabbing this is not going to have one freaking clue what that means. So the money question, this is where you're going to interpret what that means, because that's what the CEO, that's what the board of directors, that's what your boss or the decision makers are going to want to know is, what did you just figure out? You got some numbers, great, math person. What do those numbers mean? So what does it mean to say we have a confidence interval of 0.038 to 0.072? Yes? Yes. There's only one little word that I would take out of there, and that is parameter, because if you say true proportion, that is a parameter. So if that was just a little bit like you said the same thing twice, but that's the only thing that I would change about that. We are 98% confident that the interval from 0.038 to 0.072 captures the true proportion of kids who want to be a doctor. Nationwide, kids under 12, yes, get all that context in there. I ran out of steam as I was writing my answer key, but please don't let that tell you that you don't need to put all that information in there.
If you put it in percentages, would that count against you?
For a confidence interval, unfortunately, yes. So a confidence interval, they want that as decimals. All right, I think we have just enough time to do our sampling for tomorrow, and then we'll do something with our sample when we get to class tomorrow. Yes, Morgan? You could say I.
Okay.
It has to be either I or we, though. Yes. Part B? Absolutely. Is everybody okay if I go back to part B? Okay. All right. I'm going to go ahead and stop the recording for today, and we're going to take this sample.